So far we've done very simple even, odd, integer type proofs where you just plug in your even and odd, do some multiplication and addition, and it shows you that it's in the form of an even and odd. So I was thinking and I thought of, hey, what's a difficult multiplication problem? And a difficult multiplication problem is going to be a series or a factorial problem where it could be an infinite number of something, right? Because n factorial could be anything as small or as big as 1,000 or 1,000,000 or infinity or whatever, right? So the problem we're going to try and solve today is for any integer n where n is greater than or equal to 2, n factorial is always even. So the first thing you should do when you see this problem is, of course, look at some examples. And I'm going to do these in blue just because I'm not going to keep them on the whiteboard. So first we should look at 2, right? 2 factorial is going to equal to 2 times 1. Okay, let's look at 3 factorial. It's going to be 3 times 2 times 1. Oh, and these are going to be 2. This is going to be 6. Then 4 factorial is going to equal to 4 times 3 times 2 times 1, which is going to equal to 2 times 3, which is 6. 6 times 4 is 24. 5 factorial is going to equal to 5 times 3 times 2 times 1. Oh, I've missed the 4. 4 times 3 times 2 times 1. So 24 times 5, that's going to equal to 120. Okay, I think we can stop here. So just because it's going to get exponentially bigger. So based off of this, what can we see is, yeah, it looks like for numbers greater than or equal to 2, it does seem to be even. Something that also makes me believe that this is probably true is because it appears to be that any integer greater than 2, when we take the factorial of it, it's always going to have a multiple of 2, right? It's going to be 2 times something. In this case, it's 2 times 1. In this case, it's 2 times 1 times 3. In this case, it's 2 times 1 times 3 times 4. It's 2 times 1 times 3 times 4 times 5. So they're all going to be multiplied by 2, and we already know that the definition of an even number is 2 times anything, right? As long as you're not adding a 1 or subtracting a 1. So, and that's what we're doing here, we're just multiplying. So it really makes me think that this statement is in fact true. So let's try and prove it. Okay, so I've gone ahead and just moved some of the examples over here because I'm thinking I might refer back to these maybe to explain something or to see something. It's always useful to just have some examples in the back of your mind because it's difficult to think in general terms in math. So what do we do next? Next we need to know some definitions. In this case, we need to know the definition of odd and the definition of a factorial. So first let's get the even, sorry. Did I say odd? I meant even. Out of the way. So an even number is defined as an integer x such that x is equal to 2k for some k that's an integer, right? If you can write an integer as 2 times an integer, it's going to be even. Next, we need to define factorial. Now, factorials, I'm just going to say this. Factorials are going to be defined as, well, let's look at our example, right? I'm actually going to write down one more example because that might be even easier to see it might be easier to see the pattern here. 3 times 2 times 1. Okay. What do we notice with all of these factorials so far? Well, the first thing you should notice is whatever number we have in this column here, that is always going to be the very first number in our series that we're going to multiply everything by. So let's write that down. N factorial is going to equal to n. I'll put that in brackets, right? 2 factorial is going to be the first thing is 2 times yada yada yada. 3 factorial is going to be 3 times something something. 4 factorial is going to be 4 dot dot dot. 5 factorial is going to be 5 times dot dot dot. Great. What do we notice about the next number in this sequence? What do we notice about the numbers after that? These sets of numbers. Well, we notice these numbers are simply 1 less than the number before them. So this number is going to be the first number minus 1. 2 is going to be 3 minus 1. 3 is going to be 4 minus 1. 4 is going to be 5 minus 1. So it's going to be whatever this number is, subtract 1, and you're going to get your second number, right? That's how this works. So what I'm saying is to jump from here to here, it's minus 1. So let's write that down for our second product here, product element. So it's going to be n times n minus 1. Great. What do we notice about our next line of numbers? We're not going to look at 2 because we're already done with 2. Well, how do we get from here to here in all of these columns? Well, you simply subtract 1 again, right? Or you can look at it as the first number minus 2, right? That's what we're really doing here. So the second element of this product series is going to be n minus 2. Finally, because this is going to be more than enough to get the idea, the next set of numbers that we're going to multiply our series by is going to simply be, again, the previous number before that minus 1, or the first number minus 3. So it's simply going to be n minus 3. So I just moved over these numbers here. And the next thing we should notice is, okay, so we have this series that's clearly going to go on for a very long time for large numbers. So we're just going to put down 3 dots there. But how do they all end? Well, notice they all end with multiplied by 1, or 2 times 1, 2 times 1, 2 times 1, 2 times 1. So you could say, in this case, defining it as times 1, perfectly correct, perfectly accurate. But just because we are looking at cases greater than or equal to 2, we're just going to take the lowest case and say, hey, 2 times 1, 2 times 1, 2 times 1 is going to be what all these numbers have to end in, right? So we're just going to say 2 times 1. This is how we're going to define a factorial based off of just looking at the first 4 factorials in our question, right? This pattern, this rule should follow if you write this for any factorial. Okay, great. The second thing I want everyone to notice is that you can have factorials within other factorials. So 2 factorial is defined as 2 times 1. Well, what does this mean? This means that you can actually rewrite the next 3 factorials in terms of 2 factorials. So notice where we have 2 times 1, we can just replace that with 2 factorial. So 3 factorial is actually 3 times 2 factorial. 4 factorial is actually 4 times 3 times 2 factorial, and so on and so forth. Well, what else can we do? Well, next we can look at 3 factorial. 3 factorial is just going to be defined as 3 times 2 factorial. Well, that means we can define 4 and 5 in terms of 3 factorial. So what we can do is we can replace this and say this is equal to 3 factorial. And this is equal to 3 factorial. Finally, what can we say? Well, 4 factorial is equal to 4 times 3 factorial. Well, look at 5. We have 4 factorial in 5, so let's just replace that to make our equation shorter for 5 factorial. So 5 factorial is going to be 5 times 4 factorial. Okay, so notice here, this looks a lot like, let's say this column is x factorial. This looks like x multiplied by x minus 1 factorial, right? That's what this means. It's going to be whatever integer is here, subtract 1, and it's just going to be the factorial of that number. That's what we see here. So a factorial can also be defined as, if we want to simplify it, this might be useful, I don't know yet, is going to be n times n minus 1 factorial. Okay, great. Whew. Okay, now it's going to be time to start writing our proof. Now we're going to do a proof by induction, which I haven't done yet on the channel, largely because this is a very difficult question to try and prove directly by contradiction or by contrapositive. And a lot of that has to do with the fact that n factorial is kind of endless, as you see with this dot, 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 because we don't have an upper bound for n. N could be the biggest number you can imagine, and everything in between and everything bigger than that. So there's no real formalism. So instead what we're going to do is we're going to use the following logic. Because we're looking to prove for the following n, 2, 3, 4, 5, 6, dot, 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 right? we're proving for this sequence of n's. And what we want to say is this factorial is even, this factorial is even, this factorial is even, this factorial is even, and this factorial is even. The way a proof by induction works, and I'm going to try to just briefly explain the logic for this, is we say, okay, this is going to be the first digit, the fifth, so this is the first number in the sequence, the second number in the sequence, the third number in the sequence, the fourth number in the sequence, and the fifth number in the sequence, dot, 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 whatever ith number of the sequence we have. And what we're going to say is, if the first number is true, right, we're going to say, we'll call the first number x. If it's true that the first number factorial is even, we're going to prove that first. And then we're going to say, okay, this is even. Is the next number next to it x plus 1, right? To get to the second, you just add 1. Is x plus 1 also even? And this is the general part we're going to be proving. We're not going to be proving every integer up until infinity. We're going to prove the relationship that for the first number, it's going to be even, and then for the number after that, it's going to be even. And why is this a good general proof? Because after you've proven this, you can then simply make your n bigger, right? You can just say, okay, now your second number is your x, and your third number is x plus 1. But because we've already shown this, then this logic applies for all of the numbers along this series or sequence of integers that we're going to be looking at. So let's begin the proof. So I've just moved over what I've said here. Let's begin. So the first thing we're going to do is we're going to show, hey, the first number is going to, in fact, be even. The factorial of the first number is even. So we call that the base case when we're doing proofs by induction. So we write down, my bad, I completely forgot. Very first thing, it's a for all proof. What do? We write down the word let. My markers are dying on me today, so I had to switch to a purple marker for the proof. So we say, because it's a for all proof, we start with the word let. And what do we let? We first let n be an integer, and then we suppose our p here. So we say let n be an integer where n is greater than or equal to 2. Great. Now, we're going to come here, and we're going to say, let's start by showing the first number in our series here, our sequence, or whatever you want to call it, this statement holds true for. And we call this proving x is in fact even, our first number is even. We call this the base case. So we say base case. And what is the base case in our case? It's 2. Why is it 2? Because our n is greater than or equal to 2. So the lowest in the first number is 2. So we can put down in brackets n is equal to 2. So we say let n equal to 2. Then, and you can just plug this in. This is kind of more of a computational step in your induction proofs. You can say n factorial is equal to 2 factorial is equal to 2 times 1, which is equal to 2. Great. Now you can prove that 2 is even by showing that it fits this definition, that when you plug 2 into x, that k is in fact an integer. I'm not going to do that. I'm just going to assume that our reader already knows that 2 is an even number. So since 2 is an even integer, the base case is true. Awesome. So we've proven that for the first number, this statement is true. Next, we're going to show that for the next number, this is also going to be true, right? And this is where the difficult part comes in. So that was our base case. Now we're going to do what's called the induction step. Now in the induction step, it might be useful to rename your n, because as you can see here, we're dealing with n in the sequence of numbers 2, 3, 4, 5, 6, so on and so forth. But it's hard to refer to the next n as n plus 1. So it might be easier to do what I did here, where we say the first number is x, the number next to that is x plus 1. So that's what we're going to do here. I'm going to use the letter k. Let k be an integer such that k is greater than or equal to 2. And this is crucial. Since we've proven the first case is true, we can kind of do the following, which is weird. We can suppose k factorial is even. That's weird. We're supposing what we want to prove is true? Not quite. We're just restating that what we proved in the base case is true. It's not obvious yet, but it'll be obvious in a second. Let me just move this over. Okay, now so far we haven't used our definitions yet, and I think it'll be useful to define what we mean by k being even. So I'm just going to say, so k is equal to 2m, where m is an integer. Okay, so what did I say before? The reason you can suppose, we're not supposing what we want to prove is true because this is not n, this is k. We want to prove n. K is simply saying the first number. And we've shown that. Now we want to show the number next to that. So what do we say? We're going to start our next proof by therefore k plus 1 factorial. This is the key. This is what we're going to go with next. We're going to look at the sequence for k plus 1, or x plus 1 with my example here. So what is this going to equal to? Now we're going to look at our second definition for a factorial. Well, a factorial, what is the first thing that's in our factorial definition? It's simply just the number that is before the exclamation point. So we can write down k plus 1. Awesome. What is our second number? Our second number is going to be the first number minus 1. So it's going to be k plus 1 minus 1. Our second number is going to be the first number, k plus 1 minus 2. Okay? Now I'm just going to put dot, dot, dot. It's not really necessary to go this far, so we can just say dot, 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 2 times 1, since we know that all factorials end in 2 times 1. Great. Let's simplify this a little bit, right? We can rewrite this as k plus 1 multiplied by, well, k plus 1 minus 1, that's just going to be k. Next, we're going to see k plus 1 minus 2 is going to be k minus 1. And then we're going to do dot, 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 2 times 1. Okay. Where do we go from here? Well, something important for the induction step is what you supposed earlier. You're going to want to get it again. You're going to want to find it again. And what do we notice here? Well, we notice that this is exactly equal to k factorial, right? K factorial is going to equal to k times k minus 1 dot, 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 2 times 1, right? If we want to just eliminate those two and just assume the first two and the last two of the sequence. So great, what we can then do is we're getting our k factorial back that we supposed earlier, and write this as k plus 1 multiplied by k factorial. Similar to how we did here before, where this can be written as 3 times 2 factorial, written as 4 times 3 factorial, written as 5 times 4 factorial, right? Like what I said earlier in the video. That's what we're doing here. We're taking the first number multiplied by that number minus 1 factorial, which is going to be k plus 1 minus 1 factorial, which is just going to equal to k factorial. Great. What do we do next? Well, let's get rid of the factorial, right? Factorials are ugly to work with. So let's replace our k factorial with our definition for k. Oh, I'm sorry, I made a typo there earlier. It's k factorial is equal to 2m. So what we can say is k plus 1 is equal to 2m. This is amazing news. Finally, last thing I would do is I would rearrange this to 2m times k plus 1. And this is where we go back to our even and odd proofs, where we always look for an integer, right? An integer times 2. And in this case, we should see that m times k plus 1 is going to be an integer, because an integer plus an integer is an integer, multiplied by an integer is still an integer. So we say where m times k plus 1 is in fact an integer. Fantastic. Now what you want to do is you want to conclude your induction step. You want to say, therefore, or in conclusion, k plus 1 factorial is even, because k plus 1 factorial is equal to 2m times k plus 1, where m times k plus 1 is going to be an integer. So now that we've shown the first number is true, the number after that is true, we can then apply that logic in math and say, well, now we can just shift this to be our new x, and the third number to be our x plus 1. And because this is true and this is true, we can move that logic over again, x plus 1 for the fifth, and there we go. And you can just move this over until infinity, right? So let me just quickly write down the conclusion here at the very bottom. There we go. We can, of course, remind the reader that by definition of even, by definition of factorial, but you really don't need to do that. That's a lot of extra work. And we've basically have finished our proof. The rest is just like an extra sentence at the very end of another conclusion saying, since the base case is true and the induction step is true, the statement is true, right? So there we go. We have shown that for any integer n, when n is greater than or equal to 2, n factorial is always going to be even by our induction proof.